Hello guys, today I'm thrilled to present you the complete compilation of AMC 10 analysis for the 2025 AMC 10B after a whole month of work. Problem 1. A proper cup of coffee needs 20 grams of coffee beans. How many proper cups of coffee can one make with 350 grams of coffee beans? 350 divided by 20 is 17 remainder 10 or 17.5, but this isn't our answer because the problem is asking for properly brewed coffee cups, which need strictly 20 grams of coffee beans, meaning that the 10 extra grams doesn't count to anything, so we have to round down to 17 cups. Problem 2. A Pascal-like triangle is shown below. What is the sum of the numbers in the 11th row? We can notice the sum of the first row is 10, the second 11, the third 22, the fourth 44, and the fifth 88. Besides the first row which doesn't fit the pattern, the sum of the rows in this triangle are 11 times 2 to the power of n minus 2, where n is the row number. Since we're trying to find the sum of the 11th row, n equals to 11, so we can plug this in to get 11 times 2 to the power of 9, which is 5632. Problem 3. What is the sum of all the ones digit of the first 2025 positive squares? We can notice that the ones digit of the squares go 1, 4, 9, 6, 5, 6, 9, 4, 1, 0. This pattern sums to 45, but since there are 10 numbers in this pattern and 2025 isn't divisible by 10, there are 5 extra numbers, aka the remainder, namely 2021 squared, 2022 squared, all the way up to 2025 squared. Sum of the ones digit of these squares is 25, aka the sum of the first 5 numbers of the pattern. But then there are still 202 complete periods with a sum of 45, so our answer is 202 times 45 plus 25, which is 9115. Problem 4. The number of 2 digits a, b in base 7 equals to the number of 2 digits b, a in base 9. What is a plus b? By the definition of bases, a, b in base 7 equals to 7a plus b in base 10, and ba in base 9 equals to 9b plus a in base 10. So these two are equal. Simplifying this, we get 3a equals to 4b, and by base 7, a and b must be less than 7, so the only option that works is a equals to 4 and b equals to 3. Without testing though, we can get this solution by finding the LCM of 3 and 4, which is 12, and then the smallest solution for a and b is 3a and 4b equals to 12, getting the answer we just got, aka our answer is 7. Problem 5. In triangle ABC, AB equals to 10, AC equals to 18, and angle B is 130 degrees. Let O be the center of the circle containing points A, B, and C. What is the degree measure of angle CAO? So because of the fact that angle B is 130 degrees, by the inscribed angle theorem, the red major arc AC is 260 degrees, aka double that. And we can extend AO to point D such that AD is the diameter of the circle. And because of this, the orange arc AD is 180 degrees, and then the rest of it, CD, is 80 degrees. Then again, by the inscribed angle theorem, angle CAO should be half of arc CD, which is 40 degrees. Problem 6. The line y equals to 1/3 x plus 1 divides that square region below into an upper and lower region. The line XA divides the lower region into 2 regions of equal area. What is A? So first we should probably want to find the area of the red lower region, which is a trapezoid, and the area of a trapezoid is the average of its 2 bases multiplied by its height. So the length of the first base is y equals to 1/3 x plus 1. When x equals to 0, plugging this in we get y equals to 1, which is the length of our first base. Then the second one occurs when x equals to 2 at the same line, which is 5/3. The height is the side length of the square region, which is 2. Plugging this in, we get the area of the lower region equals to half times 1 plus 5/3, which is the average of the bases, times 2, which is the height, which equals to 1/3. Then we can divide this by 2 and get 4/3, which has to be the area of the main green trapezoid, which was the red one split by x equals to a. Now we can make an equation for half of the area of the lower region, which is half times 1 plus the length of the other base, which is at y equals to 1/3 x plus 1 when x equals to a. Plugging this in, we get our length of a divided by 3 plus 1. Then the height is a, and we know that this has to be equal to 4/3. And solving this, we get the quadratic a squared plus 6a minus 8 equals to 0, and a equals to -3 plus minus square root 17, but it must be plus since a has to be positive. Problem 7. Francis stands 15 meters directly south of a locked gate in a fence that runs east to west. Immediately behind the fence is a box of chocolates located X meters behind the locked gate. There is an unlocked gate 9 meters east of the box and another one 8 meters west of the locked gate. Francis has to go through an unlocked gate, and the distance for getting to the box of chocolates through both gates are the same. What is x? Francis can either go through the red or green path, and the length of the red path is the hypotenuse of the right triangle, which has a length of 17 by the Pythagorean theorem, plus 8 plus x, which is x plus 25. Then for the green path, the hypotenuse as shown is square root x plus 9 squared plus 225. Then we had to add on 9 to that, and setting these two lengths equal, we get 14x equals to 50, or x equals to 25 over 7. Problem 8. Emmy ordered 36 math club sweatshirts. The total cost was ABB.BA, where A and B are digits and A isn't 0. What is A plus B? So this problem is basically saying ABB.BA is divisible by 36. 36 can be split into 4 and 9, meaning that this number must be divisible by both. By the divisibility rule of 9, the sum of the digits of a number is divisible by 9. We get the equation A plus B plus B plus B plus A, which equals to 2A plus 3B is 0 mod 9. Then, if a number is divisible by 9, it has to be divisible by 3. 3b is already divisible by 3, so for the whole number to be divisible by 3, 2a must be divisible by 3 as well. Since a is a digit and not 0, our only options is a equals to 3, 6, or 9. We also have to note that this number is divisible by 4, and so it's even. Let's look at the number. The last digit is a, and if the whole number is divisible by 2, a has to be even. So our only option is 6. Plugging this back into 2a plus 3b equals to 0 mod 9, we get 2 times 6 plus 3b equals to 0 mod 9. And so, dividing this by 3, we get 4 plus b equals to 0 mod 3, and so b is 2 mod 3. Because b is a digit, our only options are 2, 5, and 8, and 5 is only one that will make our number divisible by 4. Problem 9. How many ordered triples x, y, z satisfy the following system of inequalities? So we can notice that all the variables are treated the same. The first inequality is all negative signs, while there are 3 after where one variable is negative. By subtracting the second inequality from the first, you get x is greater or equal to 0, and by symmetry, both y and z are both greater or equal to 0. Without the loss of generality, we can assume 0 is less than x, which is less than y, which is less than z. Then, moving x to the other side in the second inequality, we get y plus z is less or equal to 2 plus x. And from the fact that y is greater or equal to x, we can replace x on the right side of the inequality, since a 2 plus x is already greater than y plus z. Making it bigger is not going to make the inequality false. Then we can cancel y on both sides to get z is less or equal to 2, meaning that all the variables are between 0 and 2. Now we can do casework on what x equals. If x equals to 0, from the first and second inequality, y plus z is less or equal to 2 and greater or equal to 2, meaning that our only option is it's equal to 2. Then our only options for y and z respectively are 0 and 2 or 1 and 1. Then, doing the same thing with x equals to 1, we get y plus z is greater or equal to 1, or y plus z is less or equal to 3. From the statement show, y and z are between 1 and 2, so our only options are 1, 1, and 1, 2 respectively. Then finally, for x equals to 2, from the same statement shown, y and z have to be 2, and this is a valid triple. Now we need to permutate these triples. Some of these have one number different, and this number has 3 spots to be, so there are 3 ways for each of the 3 triples like this, and then there are 2 of them where all numbers are the same, and there's only one way to permutate this, and so our answer is 11. Problem 10. Let fn equal to n cubed minus 5n squared plus 2n plus 8 and gn equal to n cubed minus 6n squared plus 5n plus 12. What is the sum of integers n such that fn divided by gn is an integer? Either by using the rational root theorem or plugging in numbers and using synthetic division, we can factor fn divided by gn into n plus 1 times n minus 4 times n minus 2 divided by n plus 1 times n minus 4 times n minus 3. Canceling n plus 1 and n minus 4 on the numerator and denominator, we get n minus 2 divided by n minus 3 is an integer, and we can notice that n can only equal to 2 and 4 since that is when the denominator is 1 or negative 1. However, n equals to 4 make the denominator 0 when plugging it back into the original expression, so our only option is 2, which is our answer. Problem 11. On Monday, 6 students got randomly assigned to 6 tutors. On Tuesday, the same thing happened with the same students and same tutors. What is the probability that exactly 2 students met with the same tutor both days? So the denominator will be 6 factorials for the amount of arrangement with students and tutors on Monday. When I read this though, I was kind of confused since I thought the denominator should have been 6 factorials squared, but then you'd have to put 6 factorials on the numerator so it cancels out and gives you the same answer. Anyway, on Tuesday, there are 6 choose 2 ways to choose the 2 pairs that would be the same tutor, but the problem is asking for exactly 2 students with the same tutor, so the other 4 cannot have the same tutor without overcounting. Now to find the amount of arrangements for the other students, you can use the principle of inclusion-exclusion, but I find counting is much easier since you only end up with 9 arrangements anyway. And dividing this by 6 factorial, you get 3 over 16, which is our answer. Problem 12. Examine the figures below, all tangent congruent discs. Let T, R, and H as shown below be the ratio of the area of the disc to the enclosed polygon. Which of the following is true? We can keep the equilateral triangle as is, but we can split the rhombus in half horizontally, creating two small equilateral triangles with a disc inscribed in it. We know it's equilateral since the top angle is 60 degrees, and by the definition of a rhombus, the two sides not horizontal are equal, meaning that all angles are 60 degrees. We can then partition the hexagon, which produces the same equilateral triangles with the disc inscribed in it, and again we know it's equilateral since each split bisects the angle, creating 60-degree angles. Because they produce the same equilateral triangles with the disc inscribed in it, R and H are equal, and the only option with this is C. Problem 13. The altitude to the hypotenuse of a 30, 60, 90 triangle is divided into two segments, length x is less than y, by the median to the shortest side of the triangle. What is x divided by x plus y? The ratio for the sides of a 30, 60, 90 triangle is 1 square root 3, 2, and multiplying this by 2, we get 2 square root 3, 4. Because triangle ABC is a 30, 60, 90 triangle, the problem is only asking us for a ratio. Without the loss of generality, we can assume 2 square root 3, 4 are the side lengths for ABC. Looking at triangle ABD, we can construct line DE as shown in BM, where M is the midpoint of side AC. Then the point where CE and BM meet is a centroid, since the centroid is where the medians meet. Also, AD turns out to be 1 since triangle ABD is a 30, 60, 90 triangle and the hypotenuse is 2. In any right triangle, the median going to the hypotenuse is half the length of the hypotenuse, which is AC, which is 2. Then the centroid splits the median to a ratio of 2 to 1, so BG is 4/3 and GM is 2/3. Looking at triangle ADE, AE and AD are both 1, then since angle BAC is 60 degrees, ADE is an equilateral triangle and DE is 1. Now DE is parallel to BM because of the midpoint theorem, since E is the midpoint of AB and M is the midpoint of AC, but I just like to think of it as E and B are 1 away from each other and D and M are the same. Because of AA similarity, if we call a point where lines DB and EC meet, point H, triangles EDH and BGH are similar, which gives us x divided by y equals to 3/4, or x divided by x plus y is 3/7. Problem 14. 9 athletes at different heights are sorted into a red, blue, and green group, each with 3 people. The tallest of each group is the group captain. What is the probability the group captains are the 3 tallest people? So the denominator should be 9 factorial since that's the amount of ways to sort the athletes into groups. Note this doesn't count for order since people can be sorted into the same group in different orders, but we will account for this in the numerator so it's the same. On the numerator, the 3 tallest people have 3 factorial ways to be sorted into the red, blue, and green groups. Since the denominator doesn't count for order, the numerator shouldn't either, meaning that we have to multiply by 3 to the power of 3, since this is for whether the tallest people get sorted first, second, or third into the group that they are already assigned to. Then similar to the denominator, there are 6 factorial ways to put the remaining 6 people, which gives us an answer of 9/28. Problem 15. The sum and then summation can be expressed as A over B, where A and B are relatively prime integers. What is A plus B? The denominator of this summation can be factored as K times K plus 2 times K plus 4, and since it's a summation, we can do something called partial sum decomposition, which is where we write 1 over k cubed plus 6k squared plus 8k as A over k plus B over k plus 2 plus C over k plus 4, where A, B, and C are integers. Now getting these fractions all to a common denominator of k cubed plus 6k squared plus 8k, we can cancel out this denominator and this should be equal to 1. Now moving things around, we can factor out 1/8 and get that A equals to 1, B equals to -2, and C equals to 1 as well. Now since 1/8 is a fixed value, so the value of k doesn't affect it, and as multiplying the entire expression in the summation, we can take it out of the summation. Then plugging in increasing values of k starting from 1, we can notice that eventually 2 1/5 and 1 -2/5 cancel out. By symmetry, 1/6, 1/7, 1/8, 1/9, and everything so on cancels out as well. So all we're left in the beginning is 1 minus 1/3 minus 1/4 plus 1/2, which is 11/12. Then multiplying this by 1/8, we get 11/96, which is our answer. Problem 16. A circle has been divided into 6 different size sectors. 2 of them are red, 2 are blue, and 2 are green, so that no neighboring sectors are the same color. How many colorings are possible? Now suppose we have colors A, B, and C. There are 3 factorial ways to assign red, blue, and green to each variable. Then we want to only find structures of the colors. In short, this means that if we can obtain another structure from an existing one by just permutating the variables, we shouldn't count this new one. Without the loss of generality, assume the sector as shown is A. This is sector 1, and we can number the rest of the sectors 2 through through 6 counterclockwise. Obviously, both sectors 2 and 6 can't be A, so the other A can only go in sectors 3, 4, or 5, which is what we'll do casework on. If A is in sector 3, there's only one case and sectors 5 and 6 are next to each other and they have to be distinct, creating the structure as shown. Then, if A is in sector 4, all the variables can be opposite each other or the circle can be symmetrical vertically down the middle of sector 1, which creates 2 cases. Then if A is in sector 5, this is basically congruent to sector 3 since sector 2 and 3 are next to each other and they have to be distinct. This is one case as well, then altogether we have 4 structures and multiplying this by 3 factorial you get 24. Problem 17. Consider a decreasing sequence of n positive integers that satisfies the 2 conditions. Average of the first 3 terms is 2025. For k between 4 and n inclusive, the average of the first k terms is 1 less than the average of the first k minus 1 terms. What is the greatest possible value of n? So if we assume the nth term of the sequence is xn, the first condition translates to x1 plus x2 plus x3 divided by 3 equals to 2025, or x1 plus x2 plus x3 equals to 6075. Then we can plug in increasing values of k into the second condition. For k equals to 4, we get x1 plus x2 plus x3 plus x4 divided by 4 equals to 2024, 1 less than 2025, or x1 plus x2 plus x3 plus x4 equals to 8096. Then subtracting this from the first equation, get x4 equals to 2021, then plugging k equals to 5 into the second condition. Doing the same thing, we get x5 equals to 2019. In general, the preceding terms of the sequence are 2 less than the previous one, so if x4 is 2021, likewise, x3 is 2023, x2 is 2025, and x1 is 2027. Now we have to stop the sequence once its terms become less or equal to 0 because then it isn't a sequence of positive integers anymore. So using the formula for the nth term of an arithmetic sequence with the first term 2027 and a common difference -2, we can set this greater than 0. In solving this, we get n is less than 1014.5, but n has to be an integer, so we round down to 1014, which is our answer. Problem 18. What is the ones digit of the sum floor square root 1 plus floor square root 2 plus floor square root 3 all the way up to floor square root 2025? So floor x is the greatest integer less or equal to x. Writing out some terms of the expression, we find that in general terms n squared to n plus 1 squared minus 1 equal to the square root of n where n is a square number. Writing out the sum, we get 1 times 3 plus 2 times 5 plus 3 times 7 all the way up to 44 times 89, which can be written as a summation sigma n equals to 1 up to 44 n times 2n plus 1, which can be derived from the fact that from term n squared to n plus 1 squared minus 1, there are the absolute difference of those 2 plus 1 terms. Then we can expand and separate this into 2 summations as shown. All the squares up to n squared can be summed as n times n plus 1 times 2n plus 1 divided by 6, while all the positive integers up to n can be summed as n times n plus 1 divided by 2. Since these summations go up to n equals to 44, we can plug that into these formulas and know that we have to multiply the formula for the squares by 2 since it's 2n squared. But we also excluded a floor square root 2025, which only appears once, and this equals to 45, which we have to add onto the sum, and getting the ones digit of this, we get 5. Problem 19. A container has a 1 by 1 bottom, a 3 by 3 top, and congruent trapezoidal sides as shown. Constantly running water at a constant rate takes 35 minutes to fill up the container to the midline. How many more minutes will it take to fill up the remaining space? So one face flipped upside down looks like this, and the midline is the average of the 2 bases, which is 2. Then we can extend the bottom of the container as shown to create a pyramid, and the ratio of the volumes of the green, yellow, and blue regions are each of the bottom bases cubed, which is 1 to 8 to 27. Then the ratio of the volume already filled to the remaining volume needing to be filled, not including the extension to make the container a pyramid, is 8 minus 1, which is the red region, to 27 minus 8, which is the purple one, which is 7 to 19. Then based on this, it takes 19 over 7 more time to fill the remaining volume than the already filled up one, which is 35 times 19 over 7, which is 95. Problem 20. All the semicircles in the small circle in the middle of the square of length 1 are tangent as shown below. What is the diameter of the small circle? Let r be the radius of the semicircles and let d be the diameter of the small circle. Then the length as shown is 1 minus 2r since the diameter of the semicircle is 2r and the square has side length 1. Looking at the red triangle by the Pythagorean theorem, r squared plus 1 minus 2r plus r squared equals r squared, and solving for positive r we get square root 3 minus 1 divided by 2. Then looking at the yellow triangle with legs of r plus d and a hypotenuse of 2r, this is a 45-45-90 triangle since it's isosceles, and by the ratio of a 45-45-90 triangle, r plus d times square root 2 equals 2r, and plugging the r we already got and solving for d, we get square root 2 minus 1 times square root 3 minus 1. Problem 21. Squares in a 3x3 are colored red, blue, or yellow, so each red square shares an edge with at least one blue one, each blue square shares an edge with at least one yellow one, and each yellow square shares an edge with at least one red one. Rotations and reflections are considered the same. How many possible colorings are there? Let 1 be red, 2 be blue, and 3 be yellow. Without the loss of generality, let the center of the square be 1, and based on the edge conditions, we have the configuration as shown. Then the bottom right corner can be any color, and we'll do casework based on this. If it's 1, the middle bottom must be 2, then the left corner has to be 3, but this has to share an edge with a 1, but since it isn't, there are 0 cases for this. If it's 2 on the right corner, the middle bottom can be 1, then the left corner can be 1 or 3, which is 2 cases. If the middle bottom is 2, that's not possible, because the square after has to be 3, but there's no 1. But the middle bottom can be 3, and the left corner would be 1 or 2, so that's 2 more cases. Case 3 is if the right corner is 3, then the middle bottom is 1, and then the left corner must be 2, but there's no 3 nearby, so that's 0 cases. So in total we have 4 cases, but remember we assume without the loss of generality that the center is 1. But it can actually be any number, so there are 3 cases for the center, meaning our answer is 4 times 3 or 12. Problem 22. What is the probability that a 7-digit number is divisible by 11 given the sum of its digit is 61? So the denominator would be answering the question of how many 7-digit numbers have a sum of 61, and we notice that the maximum sum of digits for a 7-digit number is 63, whereas there are 7 nines, so we just have to take away 2 somewhere. This would be either 6 nines and 1 7, or 5 nines and 2 8s. First option has 7 choose 1 places to put the 7, which is 7 ways to order the digits of this number. The second option has 7 choose 2 ways to place the 2 8s, which is 21 ways, so the denominator is 28. Then, a number is divisible by 11 if the sum of every other digit, starting with the first one, minus the sum of the remaining digits is divisible by 11. So if we have 6 nines and 1 7, the 7 will have to go in the subtraction spots, since that would give a result of 11, which of course is divisible by 11. There are 3 subtraction spots to put the 7 in, so there are 3 numbers for this case. Then, if we have 5 nines and 2 8s, both 8s must go in the subtraction spots, since that would once again give us a result of 11. There are 3 subtraction spots, and we have to choose 2 of them, so 3 choose 2 is 3. Adding these together, we get a numerator of 6, so our answer is 6 over 28 or 3 over 14. Problem 23. A rectangular grid has 141 rows and 91 columns. Horace and Vera both fill the grid with numbers 1 through 12,831. Horace fills the grid horizontally while Vera fills it vertically, both left to right. How many squares in both grids get filled with the same number? So let x denote the column number and let y be the row number, both starting at 0. The number that Horace would fill a square in the grid with coordinates x, y is 91y, since there are y rows with 91 numbers before this row, plus x plus 1, since that's the number of squares going to the next row, then going to column x. Then Vera would fill a square with coordinates xy with 141x, since there are x columns, each with 141 numbers before the x column, and going to the next column and traveling to row x would need y plus 1 squares. Now we want to know which squares will be filled with the same number, so we should set these values equal. Then we can simplify to get 9y equals 14x, and the positions that satisfy this are 0, 0, all the way up to 90, 140, which is 11 coordinates. Problem 24. Frog moves based on these rules. It starts at 0. If it's at 0, it moves to 1 with the probability of half and disappears with the probability of half. For n equals 1, 2, or 3, if it's at n, it goes to n plus 1 with the probability of 1/4, and minus 1 with the probability 1/4, and disappears with the probability of half. What's the probability it reaches 4? Let Pn be the probability that the frog has reached 4 given that it's at n. This means that P4 is 1, since if the frog is at 4, it's already reached 4. Then we can say P0 is half P1, since the frog either goes to P1 with a half chance or disappears with a half chance and can't reach 4 anymore. Then P1 is 1/4 P0, since it has a 1/4 probability of going back to 0, plus 1/4 P2 for the same reason. After this, for the same reason, we can write P2 equals 1/4 P1 plus 1/4 P3, and P3 equals 1/4 P2 plus 1/4 P4. Now we know P4 is 1 as said, and we have 4 variables, P0, P1, P2, and P3, and we have 4 equations, and we can solve for each variable. P0 is our answer though, since we are finding the probability the frog reaches 4, given it's at 0. Solving this system of equations, we get P1 is 2 over 97, P2 is 7 over 97, P3 is 26 over 97, and P0 is 1 over 97. Problem 25. Square ABCD has side length 4 and points P and Q lie on AD and CD respectively such that AP is A over 5 and DQ is 10 over 3. A path beginning at P going to Q continues reflecting against the sides of ABCD with congruent incoming and outgoing angles. If the path hits a vertex of ABCD, it stops. What vertex makes a path stop? We can do something called reflecting over, meaning that we let the line continue till it hits a vertex of ABCD, and that's the answer to our problem. We first want to find the equation, therefore slope of this line. If we set A as the origin, P is 0, 8 over 5, and Q is 10 thirds 0. Then since the line passes both of these points, the slope is 18 over 25, and the equation is y equals 18 over 25x plus 8 over 5. Then each vertex of ABCD is in the form 4m, 4n, where m and n are integers since the side length of ABCD is 4. Plugging 4m into the equation, we get y is 72m plus 40 over 25, and the numerator is divisible by 25 since the whole fraction has to be an integer. We can divide the numerator by 4 since 25 isn't divisible by 4, and simplifying we get m is 5 mod 25, meaning the smallest value of m that works is 5, and x is 20 and y is 16. Now I want to figure out which vertex is at 20, 16, and we can draw 5 squares to the right, which gives x equals 20, and 4 squares up, which gives y equals 16, and labeling each of these vertices based on the square that was given, we get the line hits B.